We're asked to find the critical points and linearization of the given nonlinear system. We have x prime equals the square of x minus 1 plus y, and y prime equals x squared plus y. Referring to our notes, this indicates that f of x comma y is equal to the square of x minus 1 plus y, and g of x comma y is equal to x squared plus y. The critical points occur where both f of x comma y and g of x comma y equals 0, which means to determine the critical points, we need to solve the system the square of x minus 1 plus y equals 0, and x squared plus y equals 0. To solve the system, let's square x minus 1 in the first equation. This gives us x squared minus 2x plus 1 plus y equals 0. And since the second equation indicates that x squared plus y equals 0, we can substitute 0 for x squared plus y, and the equation simplifies to negative 2x plus 1 equals 0, and therefore x equals 1/2. And then if we substitute x equals 1/2 into the second equation, we have the square of 1/2 plus y equals 0, giving us y equals negative 1/4. This is the only critical point of the system. Now that we've determined the critical point, we can perform the linearization. We first change the variables. We let u equal x minus x sub 0 and v equal y minus y sub 0, where x sub 0 comma y sub 0 is a critical point. This indicates that u is equal to x minus 1/2 and v equals y plus 1/4. Next, we determine the Jacobian matrix, where in the first row we have the partial derivatives of f, in the second row we have the partial derivatives of g. So again, we have f of x comma y equals the square of x minus 1 plus y, and g of x comma y equals x squared plus y. This indicates for the first row of the Jacobian, we have the partial of f with respect to x, which is 2 times the quantity x minus 1, and then we have the partial of f with respect to y, which is just 1. In the second row, we have the partial of g with respect to x, which is 2x, and then we have the partial of g with respect to y, which is 1. And now we evaluate this at the critical point 1/2 comma negative 1/4, which gives us the 2 by 2 matrix with entries negative 1, 1, 1, 1. And now we have the information we need for the linearization when u equals x minus 1/2 and v equals y plus 1/4. We have the derivative of the vector uv equals the 2 by 2 Jacobian with entries negative 1, 1, 1, 1 times the vector uv. This indicates with u equal x minus 1/2 and v equals y plus 1/4, the linearization is u prime equals negative u plus v, and v prime equals u plus v. Before we go, let's look at the slope field for the original system as well as the linearization. On the left, we have the vector field for the given system. Notice how it does indicate the point 1/2 comma negative 1/4 is a critical point. On the right, we have the linearization near x comma y equals 1/2 comma negative 1/4, which is the same as u comma v equals 0 comma 0. When performing the linearization, recall the coordinate system uses u and v, not x and y, which is why when performing linearization, the critical point will always appear at the point 0 comma 0. Analyzing both the original slope field and the slope field of the linearization, notice how the linearization is a good approximation of the original slope field near the critical point. I hope you found this helpful.